Okay, so let's go back to answer the question. And I will use the example I gave in my teaching in Math 2E to illustrate things. So I teach Math 2E, which is the multivariable calculus. I taught it last year. And this is a typical problem I gave to my students, to the students. So we teach Math 2E to freshmen and sophomore, and the students are taught to learn how to do triple integral. So this is a typical problem I gave to students. So integration over W, where W is a three-dimensional object, which is defined, which is bounded by several planes and surfaces. So one plane is x equals 0. So suppose we are in the x, y, z coordinates. So one is x equals 0, y equals 0, and z is equal to 2. And then the surface is z equals x squared plus y squared. So these four surfaces just bound the region W, and the students are trying to compute the integration. So students are taught to learn how to draw the picture. So the major difficulty of this problem is not the calculus itself, it's not the integration itself. The most difficult part of this problem is the students should learn how to draw the picture, okay, of this region. So this is the picture of the region W. Okay? And so you see, the problem becomes easy if you can actually see what the region is. When you draw the picture and you look at it, you completely understand what it is. And then you can take integration using a fairly routine way. We teach students that. So the problem is that in differential geometry, we seldom study such a three-dimensional object. Okay? We study some object. We study integrations over an object which is n-dimensional. In particular, we are more interested in high dimension more than 3 than other lower dimensional case. So the problem is that we cannot draw the picture because no human being can imagine anything bigger than 3 dimensional. So that's the problem. Okay, how to do that? So if suppose we still want to do integration and we cannot draw the picture, what should we do? So that's the question. So here is the picture of the so-called Calabi-Yau threefold. So a Calabi-Yau threefold is a 6-dimensional object, which I said we cannot imagine that. But this is the picture I got from the internet. Is the intersection of this 6-dimensional object, whatever it is, to the 3-dimensional space. Okay? And the intersection is a 2-dimensional surface. And by looking at it, you see how complicated this even 2-dimensional object is. And you can imagine, this is just the projection of a 6-dimensional object to our world. And the 6-dimensional object is much more complicated than we can solve. Okay? So there's a need, at least there's a need in physics, in string theory, to study the so-called,